Hello, welcome to our next section, Best Practices. After working on multiple projects covering important machine learning concepts, techniques, and widely used algorithms, we have gathered a broad picture of the machine learning ecosystem and solid experience in tackling practical problems using machine learning algorithms and Python. However, there will be issues once we start working on projects from scratch in the real world. This section aims to get us ready for it with best practices to follow throughout the entire machine learning solution workflow. So, we will learn the best practices in the data preparation stage, the training sets generation stage, the algorithm training, evaluation, and selection stage, and also in the system deployment and monitoring stage. Now we move on to the first video of this section that deals with the best practices in the data preparation stage. In this video, we will understand the project goal, collect all the fields that are relevant, and see how to maintain consistency of field values and deal with missing data. In general, tasks in solving a machine learning problem can be summarized into 4 areas: data preparation, training sets generation, algorithm training, evaluation and selection, and the last one, deployment and monitoring. Starting from data sources to the final machine learning system, a machine learning solution basically follows the paradigm illustrated with this diagram. So we will be learning about the typical tasks, common challenges, and best practices for each of these 4 stages. Apparently, no machine learning system can be built without data. Data collection should be our first focus. Before starting to collect data, we should make sure that the goal of the project, the business problem, is completely understood, as it will guide us to what data sources to look into and where sufficient domain knowledge and expertise is also required. With a goal to achieve in mind, we have narrowed down potential data sources to investigate. Now the question becomes, is it necessary to collect data of all fields available in a data source, or is a subset of attributes enough? It would be perfect if we could know in advance which attributes are key indicators or key predictive factors. However, it is very difficult to ensure that the attributes handpicked by a domain expert will yield the best prediction results. Hence, for each data source, it is recommended to collect all fields that are related to the project, especially in cases where recollecting the data is time-consuming or even impossible. For example, in the stock price prediction example, we collected data of all fields including open, high, low, and volume, even though initially we were uncertain of how useful high and low are. Retrieving the stock data is quick and easy with the API though. Now let's see how to deal with missing data. So due to various reasons, datasets in the real world are rarely completely clean and often contain missing or corrupt values. They are usually presented as blanks, null, -1, 999999, unknown, or any placeholder. Samples with missing data not only provide incomplete predictive information, but also might confuse the machine learning model, as it cannot tell whether -1 or unknown holds a meaning. It is significant to pinpoint and deal with missing data in order to avoid jeopardizing the performance of models in later stages. Here are the 3 basic strategies that we can use to tackle the missing data issue. Discarding samples containing any missing value. Discarding fields containing missing values in any sample. These 2 strategies are simple to implement, however, at the expense of lost data, especially when the original dataset is not large enough. The third strategy does not abandon any data, but tries to fill in the blanks, inferring the missing values based on the known part from the attribute. The process is called missing data imputation. Typical imputation methods include replacing missing values with the mean or the median value of the field across all samples, or the most frequent value for categorical data. Let's look at how each strategy is applied in an example where we have a dataset of age and income, consisting of 6 samples. If we process this dataset using the first strategy, that is, discarding the samples, it gives data as this one. If we employ the second strategy, the dataset becomes as this set, where only the first field remains. If we decide to complete the unknown value instead of skipping it, the sample 35, unknown can be transformed into 35,72 with the mean of the rest of the values in the second field, or 35,70 with the median value in the second field. In scikit-learn, the imputer class provides a nicely written imputation transformer. Let's go to the Python command prompt and use it for the previous small example. Import NumPy and imputer. Next, we create an array, data origin. Here we have represented the unknown value by np.nan in NumPy. Then we initialize the imputation transformer with the mean value. And obtain such information from the original data. Once this is done, complete the missing value. After this, we print the updated data. Here's the modified array. Similarly, we initialize the imputation transformer with the median value and obtain the values from the original data. We again complete the missing value with the median value and print the updated data. You can see that the missing value has been replaced with the median value. When new samples come in, missing values can be imputed using the trained transformer. Let's see how it is done. So we define a new array with these values. We use the trained transformer for imputing the missing value and print it. You can see the output here. Note that 30 in the age field is the mean of those 4 age values in the original dataset. Now that we have seen how imputation works and its implementation, let's see how the strategy of imputing missing values and discarding missing data affects the prediction results through the next example. Let me clear the screen. First, we import the dataset and then load the diabetes dataset. Let's define X, full, and Y variables and store data and target respectively in these variables. And now simulate a corrupted dataset with missing values. Then we print M and M missing values. Let's first set the seed and then randomly select M missing samples with this line of code. Next, we shuffle the missing samples. Now for each missing sample, randomly select 1 out of n features. Represent the missing values as NaN. For that, let's first copy X full as X missing, and then replace the missing values with NaN. Oops, it's features and not feature. My bad. Let's run it again. Done. Then we deal with this corrupted dataset by discarding samples containing a missing value. We then measure the effects of using this strategy by estimating the averaged regression score, the R-square, with a regression forest model in a cross-validation manner. For this, we first import the random forest regressor and cross_val_score models. Initialize the random forest regressor object. Next, we calculate the cross-val score and store it in the score RM missing variables. And lastly, print the score of the dataset with missing samples removed. So, here's the score. Now we approach the corrupted dataset differently by first initializing the imputer class and then imputing missing values with the mean. And similarly, we measure the effects of using this strategy by estimating the averaged R-square. So again, we initialize the random forest regressor object. Next, we calculate the cross-val score. After that, we print the score of the dataset with the missing values replaced by the mean values. You can observe the change in the score. Imputation strategy works better than discarding in this case. So how far is the imputed dataset from the original full one? We can check it again by estimating the averaged regression score on the original dataset. Let's repeat our previous step on the original dataset. Also, we print the score again. So it turns out that little information is comprised in the completed dataset. However, there is no guarantee that the imputation strategy always works better, and sometimes dropping samples with missing values can be more effective. Hence, it is a great practice to compare the performances of different strategies via cross-validation, as we have practiced previously. In this video, we have learned the best practices in the data preparation stage,